Hi, good day dear audience. This is the second episode in my series of videos relating cardiology to fluid mechanics. In this video we would be studying the non-steady state flow equation, or the generalized non-steady state flow equation. Generalized because it could be used for gases as well as liquids, and for elastic bodies where the area changes by time. This is a 6 terms equation, as you see: 1, 2, 3, 4, 5, 6. This is rho, the density, partial v by partial x, the change of velocity with distance at the given time, plus rho g over a, acceleration of gravity over the shock wave speed in the media. We'll discuss it soon, later, or very soon. dz by the x, the change in height with distance. For a horizontal tube or pipe or a blood vessel, dz by the x is logically 0. There is no change in height with distance. For a vertical pipe, dz by the x is 1. If you remember trigonometry, if a pipe or a blood vessel or whatever is inclined by 45 degrees, then dz by the x by the triangle ratio would be 1 over root 2. V partial rho by partial x, the change in density with distance, plus rho v over a, the present area, partial a by partial x, the change in area with distance, plus rho over a, partial a by partial t, that is the change in area for a given section by time, the section under study, plus partial rho by partial t, the change in density with time. What is A? A is the shock wave speed through the media. Actually, the sound is a shock wave. A for air for a shock wave is nearly 340 meters per second, the speed of sound. But here our media, how it is calculated, we'll soon see. It is the square root of the modulus of elasticity of the material divided by the density, under the root, of course. That's simply what is A. Here, don't get shocked by the 6 terms equation. Why? Because we'll soon get rid of 2 terms being equal to 0. Partial rho by partial t. This is a liquid, not a gas, so the density doesn't change with time, so nor with distance. So this term and that term would be cancelled. We would left with these 4 terms, and as for these terms, they are equal. This equation is equated to 0. And both of these 4 terms are multiplied by rho. Here is rho, and rho being constant, and the equation equated to 0. So if we divide it by rho, we divide the 4 terms by rho, equation would be correct. So here we would be left by partial rho by partial v, plus or minus g over a dz by the x, plus v over a partial a by partial x, plus 1 over a partial a by partial t equals 0. Why plus or minus? Because the sonic shock wave moves forward and backwards. So in the forward path it is plus, in the backward path it is minus. Here is our numerical example for the carotid artery. There are 2 carotid arteries, one on the left of the neck and one of the right of the neck. It is of approximate diameter 6 millimeters, and average flow rate during the pulse, the left ventricle pulse, of 7.5 cubic centimeters per second. The area, in case of 6 millimeters, that's 0.006 meters, the area would be 2.827 times 10 to the power minus 5 meters square. As I said, our system is the MKS system, where the length meter, the area meter square, and so on. The flow velocity would be, flow rate over area would be 0.265 meters per second. Of course, in the carotid artery, the flow is from down to up, the flow of blood from the heart to the brain. Let's start our origin section in the differential equation at A1, at the bulged section due to the shock wave created by the left ventricle. From the continuity equation, we can calculate the V, assuming the bulged section is of area 7 times 10 to the power minus 5 meters square, from the continuity equation, knowing that the flow is 7.5 cc's, that is 7.5 times 10 to the power minus 6 meter cube per second. The velocity would be 0.107 meters per second. And applying the partial differential equation, but with positive sign because we are in the forward path, we get that the original velocity being 0.107 plus 9.8, that is g over a times dz by dx. Because the pipe, the blood vessel, the carotid artery is vertical, so dz by dx equals 1. 9.8 g, the acceleration of gravity, over a as calculated here from the E for the carotid artery material is 9,000 pascals, while rho for the type of blood vessel of the carotid artery is 1,200 kilogram per meter cube. That is 1.2 grams per centimeter cube. We get 2.738, and substituting it here, plus v over a, that's the original velocity at the bulge section, which we considered it our origin of calculation, over 7. Here I am not calculating the real values, because a and a being multiplied to transform it to meter square, I am just putting 7 and 2.287 minus 7. That's the original, the second section area minus the present section area, the bulged section, but not multiplying, but by the real value 10 to the power minus 5 to convert it to meter cube, because 10 to the power minus 5 here would be cancelled to 10 to the power minus 5 here, over dx, which is 0.08, plus 1 over a. Here I am obliged to put it in real numbers, in the real value. Why? Because partial a by partial t is a unit with in its own. If this were also expressed in area, I could have made the same thing. And apply and substituting, I get 1.975 plus 3.58 minus 0.9 plus 1 over 7 times into partial a by partial t equals 0. And substituting these three values would become 4.655 equals, transferring to the other side would get minus 1 over 7 times 10 to the power minus 5 to partial a by partial t, from which partial a by partial t equals minus 32.6 times 10 to the power minus 5 finally, which is equal to 3.26 centimeters, converting it to the level of the blood vessels, minus 3.26 centimeters square per second. What does this mean? This is that the bulge section is now contracting with time by speed of the area is contracting, is losing its area and returning to non-bulged form by 3.26 centimeters per second, but with a decrease. That's why the minus sign. So that's clear. I think things are very clear here. If this were the backward shock wave, we would have found this positive, that is, the section is bulging on the return of the bulging and return to the original section of the blood vessel doesn't affect the velocity actually, but it affects it locally, but doesn't affect the flow by increase or decrease. But this is an example, and with real values. I hope it is understandable. That's all for today. Thank you, dear audience.